So that video title is a bit of a lie, and I kind of feel bad for doing that. But here's the thing: when it comes to cryptographic algorithms that are actually being used, none of them are actually secure. And the reason for that is because there is only one mathematically proven secure cryptographic algorithm, and that's the one-time pad. But it's not really usable unless you want to double the amount of data that you're sending to a client, and you also have some way of distributing the key to your client without sending it through the same channel. So what is a one-time pad? Well, one-time pad is basically you take your message, you get a perfectly random key that is exactly the same length as your message, and then you do some sort of XOR, or you do some sort of shift on that key to the message, and then that gives you your encrypted message, right? Why does that work? Well, it works because the answer space and the message space are the same size, and because of that, the space of the encrypted message is the same size as the space of any message of that length, right? And the reason for that is the pigeonhole principle, but I'm going to explain it here with flowers. So I'm standing here in a field of flowers, right? You can see all around me there are tons and tons of wildflowers. Now, if we say that every single one of these wildflowers needs to be pollinated by a single bee, that is, a bee needs to land on the flower and distribute its pollen into that flower, the amount of bees, if the amount of bees is smaller than the amount of flowers, it is guaranteed that a single bee goes to one or more flowers. That's called the pigeonhole principle. And the pigeonhole principle originally was used to describe pigeonholes, and exactly the same scenario. If you've got 10 pigeons and 5 pigeonholes, there's one hole that's going to have multiple pigeons in it, at least, right? Now, with messages and message spaces, with a one-time pad, your message space and the encrypted data need to be the same size in order for the message to be truly cryptographically secure. Hi, howdy. So all my footage is super blurry from the rest of that walk, but essentially what I was trying to get across is this. With a one-time pad, your message and your key are the same size, so they both encode the same amount of information. When you apply your cipher, that means that you have exactly the same amount of entropy in your key as you do in your message. So the encrypted message cannot be mathematically proven to be the original message, because the encrypted message contains every possible input message given whatever key, right? So basically you can go both ways, right? The message and the key have to be given together in order for you to get the last one, and there are multiple possible answers, right? With modern cryptography, what we're doing is we're essentially saying we don't want to have to do that. We want smaller keys so that we can distribute them easier, but we want to make it secure enough so that any large-scale attacks are infeasible. Not impossible, infeasible. And what infeasible means is it means that somebody with a large enough computer can't compute it in a reasonable amount of time. And the definition of reasonable changes depending on what attacker you're talking to. If you're talking about nation states, if you're talking about individuals or companies, right, the answer is going to be very, very different. However, with the size of the keys that we're up to nowadays, the reality is that it's infeasible to break any of these cryptographic schemes. So are the schemes actually secure? Well, with a big enough computer, no, they're not. However, they're secure enough for use. And that's what modern cryptography is really based off of. And that's what I was trying to get across in this video, is essentially that Cryptography is not perfect. It's a balancing act between infeasible and good enough, basically. So that's today's video. Thank you.